Hello everyone, welcome to my YouTube channel. I'm ABAQUS and I'm thrilled to have you here. As a PhD in mechanics, I'm passionate about sharing my knowledge and expertise in finite element simulation using ABAQUS. Thank you for joining me today, and let's dive right into the exciting world of finite element simulation with ABAQUS. In this video, we are going to simulate a damage phenomenon of a real adhesive joint. We are going to use the cohesive element method, or as an abbreviation, we are going to use the CZM method to our simulation. It is going to be a real tutorial. Then I use my previous result of my research here. As you can see, we have made some dumbbell shape of the adhesive specimens. So we use these dumbbell shaped specimens to obtain a stress strain curve of the adhesive. Then we have manufactured some single lap joint specimens, as you can see in this figure, and also you have seen the dimensions of the single lap joint we have used in our research. So after getting let me see the references. So after we getting the stress strain curve of the dumbbell shape, we use the result of this curve to obtain the load displacement curve of the single lap joint that you can see the shape here. The results obtained from two papers of us. The first one is the effect of reduced graphene oxide on mechanical behavior of an epoxy, which published in the Journal of Composite Materials, and this curve obtained from the article in the title of Creep Behavior of a Graphene Reinforced Epoxy Adhesively Bonded Joint, which is published in the Journal of Adhesion. So we are faced completely with a real tutorial. So let's go to the simulation part. First we open the ABAQUS software, then we go to the part modulus, then we create a part from this bottom. The name, we enter SLJ. It is a 2D planar model. It is deformable and the future is shape. Since we are going to model it as a 2D shape model, 2D SLJ, then you should choose these features for that. Press on continue and follow me to model SLJ. Completely, you need to draw a schematic model of SLJ, as you can see here. Then you had to add some constraint from this button. Click on this and choose equal lengths. And we choose the equal length lines. These are mm, the equal lengths, and also the overlap lengths should be equal, and also the adhesive thickness should be equal in the both sides. Also the thickness of the adherent, which is aluminum here, should be equal. The constraint have done, then we are going to measure the length. As you can see in this figure, we have here the dimensions. The overlap length is 15 millimeter. The thickness is 0.2, and this length of the adherent is 85. Then we have set the dimensions. So here is 15, it's okay. And this length should be 70. Adherent thickness is 2 millimeter. It is not allowable, then I push Ctrl Z to remove that part, and I try from the other side. 2 millimeter here, and also the thickness of adhesive, which is 0.2. So it's okay. Push the middle bottom of the mouse so you can see the feature of the SLJ. And now we have to make some partitions. We use partition face, click on that. I made some partitions from here to here. As you know, we made these partitions to separate the adhesive layer from the aluminum part. Also we made some partitions to simplify the meshing feature in the meshing module. We made these partitions on the SLJ shape, then everything is done. Click on the middle bottom, then go to the property module. As I told you, since we have faced a real tutorial, we have to use the right material properties. So we go back to our results. The black line here is related to our simulation, and this is the material property of the adhesive. So from this type of the stress strain, we cannot use it as a traction separation property of the adhesive. And then we have to make some change in the stress strain curve to make it appropriate for traction separation model of the single lap joint. The most important of which is changing the strain of the stress strain curve to the displacement. So we have to multiply the strain here to the thickness of the adhesive in the SLJ model, which is 0.2 millimeter. Then we multiplied 0.2 to the strain, and we obtain this curve. Okay, now we have stress displacement curve. and we can use it as a material property for the traction suppression cohesive element. For that, we made some simplification on this curve. First, we assume that these curves linearly increase from the 0 to its topmost, its maximum amount, which is 26 megapascal, and then it goes in the line shape, in the constant line shape, and here it comes down, and the rupture, which is here, which here is the rupture point, and from this point the rupture occurs. So here we have the damage parameter equals to 0, and here we have the damage parameter equals to 1. So here, as you can see here, the slope of this line is equal to 8,000 newtons per millimeter. However, if you see here, the slope is 1600 megapascal, and then you have to change this curve to this curve. So the traction suppression Young modulus will be 8,000 Newton millimeters, and also you can obtain G parameter for traction suppression element from the following equation, which is for the isotropic materials. If you calculate this amount, you will see that G will be equal to 2860 Newton per millimeters. It is noteworthy that new parameter is equal to 0.35 for this adhesive. After speaking about the slope of this line, and then we reach the maximum amount of stress that the adhesive were able to bear, which is 26 megapascal, and this amount is the damage initiation amount, 26 megapascal. And also the final and the third important parameter in the traction suppression law is the energy at failure. This energy at failure is the integration or the area of this rectangle. As you calculate this amount is equals to this length multiplied to this length, then it is almost 0.08 multiplied to 26, which is 2.86 newtons per millimeter. So we insert these material properties to the ABAQUS. For the first material, we have aluminium. The name is aluminium material. Choose the elasticity, elastic. It is an isotropic material. I mean the aluminium part. The Young modulus is equals to 70 gigapascal, but however we use the dimensions by millimeter, we have to use 70,000 megapascal, and also enter 0.35 for the Poisson ratio of the aluminium. Click OK and made another material, and here we have adhesive. Choose material, elasticity, and elastic. As I told you, we are going to use the traction separation element, then we change the type of element, type of material to traction. So we have the slope of the stress displacement curve as you heard, 8000 for E and 2860 for G. It means 8000 for E, and from the two shear properties you can enter 2860. Okay, then we have to enter the damage properties of the adhesive. You can go to the damage of traction separation law and click on damage, on quads damage. On the quads damage you can enter the maximum amount of stress that the material can bear without failing, without starting the damage phenomenon. As you can see in this figure, I mean this point, the amount of this point, which is 26 megapascal. Also, it is not forced that this curve is for tensile properties, and also it is a good assumption that you use the same property to the shear load, then we are allowed to enter 26 and 26 and 26 as the quads damage parameter. So in the next step we have entered the energy at failure. You should come to this window, change the type to the energy, and the type of linearity is the type of softening is linear, and degradation is maximum, and don't change these options and just enter the fracture energy as we calculated, 2.08. Click on OK. Also click on sub options of the damage properties, click on damage stabilization cohesive. So in this window you should enter a very short amount like 0.0001, which is not very important in the result part. However, it's important to get the convergence of the problem, but 0.0001 is a good amount for this section. Click on OK, and also click on OK to close the window. Then you have to create some sections. We have two sections here, aluminum and also the adhesive part. Click on that, and the name is aluminum. The first part is the solid, and also it is a homogeneous material. Click on OK, choose aluminum from this window, and enter 15 as the thickness of the SLJ sample. Click on OK to close this window. Then once again create another section, which is adhesive section. the adhesive section is a cohesive element, and in the category part you should go to the others and choose the cohesive here. Click on continue. We have adhesive. We have to adhesive. We have to continue. Yes. Okay, we made a new section. The section's name is adhesive. Continue. Material is adhesive. Okay. Missed value. We have to okay, then we go to make another section. Click on create section, and the second section is adhesive section, which is a cohesive element. Then on the category, go on the others part and click on cohesive and click on continue. The material is adhesive and the response is traction separation. And also you have to click on auto plane thickness and enter the thickness as 15 millimeters. So click on OK. We now made two sections, adhesive and aluminium, as you can see here. And then we have to assign our sections to the parts. Click on assign section, choose the aluminium here and choose the aluminium here, and let the aluminium part turns to green. And also we have to select this layer, adhesive layer, and click on the middle button, choose adhesive here and click OK. Then we have whole model turns to green, which means that the whole model assigned the real properties. Then we go to the assembly part. We click on the create instance. We enter the SLG model here and we click OK. Go to the next step. On the step modulus, create one step. Our problem is going to solve using static general method. Then click on OK and continue. It will be an nonlinear geometric problem. Then click here and go to the incrementation part. We set the first increment size equals to 0.05 and the maximum amount which is 0.2. Click on OK, then goes to the field output and click on edit part. Here we can choose some field output that we are going to see the results in the visualization module. Then we click on failure and fracture, and here scalar stiffness degradation. You can choose this one, and also you can go to the status and choose the status part here and click OK. and also you can click dismiss to close this window. Now we can go to the interaction modulus. Here to obtain the load displacement curve, it's better to make a reference point and couple this line features to that reference point. So we can make this reference point, for example here, click here, and then click on the create constraints and use the coupling, continue, click on the reference point, OK, and choose the surface and choose this line as a surface coupled with the reference point. As you can see, these features U1, U2 and rotational U, and rotational U is coupled by the reference point. The line and reference point coupled to each other by this method. Click on OK. Then we can go on the load modulus. In the load modulus, we have boundary condition. You can use in caster. Click continue. Choose this line and use the incaster. Click on OK. And for the other side, click on boundary condition and use displacement rotation. Click on continue, and here you have to choose the reference point. Choose the reference point, click on middle bottom of the mouse. Then here we choose that this point, which is represented of the line here, goes 1 millimeter or maybe 0.5 millimeter toward U1 direction. Click on OK, and you can see here we have the load. Then we can go to the mesh part. Click on the part, and first you can make a seed on the model. Click on the seed part. Approximately global size, you can change this to 0. Maybe 0.2. Maybe it's good because our thickness is 0.2 also, or maybe 0.5. Click on OK. Then we want to have the mesh shape of rectangle here, and then click on assign mesh. Click on assign mesh and choose the whole model. And here we have structural and element shape, which is quad. Click on OK to turn the model into green. Then we have to assign the element type of each area. So click here on assign element type, choose the aluminium part, mid click on the mouse, and here we have to select plane strain part and click on OK. And also once again the adhesive layer, which is a cohesive element type. Here you can choose the element controls options. You can change this, for example viscosity, as we have set in the property part. You can set it on 0.0001, which is a very short amount. As we said before, it deals with the deal with the convergence of the problem. And element dilatation, yes, and maximum degradation. If you choose, for example, if you want to specify it and set it on 0. For example, 98. If your damage parameter equals to 98, 0.98, the software is going to delete that element. And also we have here scale factor, which is just for your vision. It is not going to change your result, but if you set this part to, for example, 0.1, you can see a better visual of your deformed shape of your SLJ. So we set it on 0.1, click on OK part, then everything is done, and now it's time for meshing. Click on mesh button and click on yes. Okay, we have our model meshed like this. Then we go to the job modulus. We create a new job. The name is SLJ damage. Click on continue. Okay, then click on submit to let to the software solving the problem. You also can check the iteration here from the monitor. Okay, everything is done, and we can go to the result part. Okay, as you click here, you can see the result. Here is the Omises stress. Exactly like this. Okay, and also as you remember, we select status, which show the real cohesive elements that, for example, in the step time 0 is like this, and it removes like this. It removes like this, and also you can see the damage parameter we selected from the field output, which is STEG. Here, as you can see, the damage parameter in these elements is equal to almost 0.94, and we entered the 0.98 element will be deleted. So you can see here as it reached to the 0.98, the element will be deleted here. Okay, but the most important part is the load displacement curve, the load displacement curve of the SLJ. So here we go to the create XY data. We are going to make the diagram of the load displacement curve. Click on here, this button, and click on ODB field output. Click on OK. Then go to the unique nodal. Here you have to select reference reaction forces and reaction force on the one axis direction, and also U similarly on the one direction, which is here X direction. So you can select this tab, and from here edit selection, you can choose the reference point that we have here. Click on save and click on OK. You can close this window, and now you should operate the datas. So come here to XY data management, click on that, and here come here to create XY data and click on operate XY data, click on continue, then here choose combine and click combine U, press comma, and then RF, and you can also save this as load displacement, load displacement curve. Click on OK and you can make it. So you also can plot this curve, plot here, and you will see the result. Okay, exactly like this. You also can create a new viewpoint and parallelly use the results. Okay. Okay, like this. If I decrease the rate, you will see better maybe. The load is increasing up until the top point, and then the damage parameter starts and remove the cohesive elements, and then you will see the decrease of the load here, like this. Okay. You also can obtain the data of this load displacement curve using here. Click here and double click on this part, load displacement, as we created before, and select these part and copy this and use it to your Excel file as well. Okay. Here, as you know that we obtained this curve from our results of this article, which is this curve, the black line. Here we are going to face these two curves to each other to have a verification to our results. As you can see from the both curves, the green curve is related to the FEM results, and the red curve is the experimental part of our results. So as you can see, we have a comparable amount of maximum load, a maximum load which is equals to 5,000, around 5,000 newtons, and these two results are very near to each other, simulating the maximum amount of load that the single lap joint can bear. So, however, about our displacement, you can see that the results of FEM is not comparable with the FEM with the experimental results. As one reason, we can tell that since we don't use the accurate measurement for our displacement, maybe the experimental part is a bit out of real amount, and for obtaining a more accurate result, maybe it's better to use the more accurate method in the experimental part, as you can use the right extensiometer also, or maybe you want to use high-speed camera or DIC method like that. However, this is the simulation video of the damage, and this is a real damage simulation. You also can find me on ResearchGate, and if you have any question, feel free to write it on the comment section, and I want to be a hand of your learning career. Hope doing great. Bye.